Solving a system of linear equations by Gaussian elimination. The first step in solving our system is to express it as an augmented matrix. In this example, we'll be dealing with a system that has 3 equations and 3 unknowns, x1, x2, and x3. We know that we can rewrite this system as a statement of matrix multiplication, where the coefficients times the variables equals the constants on the right. When we write our augmented matrix, we only include the coefficients and the constants, and usually draw a line to distinguish between the two. Now that we have our augmented matrix, it's time to start forward elimination. Forward elimination is the process by which we try to convert a specific part of the coefficient matrix to 0. In particular, we want all of the coefficients underneath the diagonal line to be 0, everything in this red triangle. We do this in a very systematic manner, working by columns from left to right, and within each column, starting at the bottom and working our way up. So first, we'll begin with the first column, eliminating the 6, and then the 5, and then we'll move on to the second column, eliminating the 1. If it were a larger matrix, you would continue in the same pattern. Let's start by eliminating the 6. How will we do this? Well, we know that it's legitimate to add and subtract multiples of equations from each other. What if we could add a multiple of a different row to this row in such a way as to cancel out the 6? In order to do this, we'll need to find the pivot value. The pivot value is the coefficient that's in the diagonal of the matrix and above the value you're trying to eliminate. In that case, this would be the 4, since it's the value in the diagonal that is above the value we're trying to eliminate. When you divide the value you're trying to eliminate by the pivot value, it creates something called the pivot coefficient. This will be useful in our equation for determining the new row to replace the row the 6 is in. The new row will be equal to the old row, the values in the old row, minus the pivot coefficient times the pivot row, the row that our pivot value is in. So writing this out, the new row that we'll use to replace 6, 1, 1, 6 is equal to the old row minus our pivot coefficient, 6 over 4, times the pivot row, 4, 1, negative 2. Let's go ahead and see how this works out. We leave the top 2 rows the way they were because it's only the bottom row, the row with a 6 in it, that we're trying to replace. Each value in this row we replace by taking the value in the old row and subtracting the pivot coefficient, 6 over 4, by the corresponding value in the pivot row. When you do all the math, we end up with this, our new matrix. So we've eliminated one value. That's great. The 6 has been changed to a 0. We need to keep on working our way up in this column. Next, we need to eliminate the 5. So once again, we apply the same formula. The new row that we'll use to replace 5, 1, 2, 4 is equal to the values in the old row minus 5 over 4, our pivot coefficient, times the value in our pivot row, 4, 1, negative 2. How do we know our pivot coefficient is 5 over 4? Well, once again, it's the value you're trying to eliminate over the pivot value. So when we go ahead and write this out, we have our old values, 5, 1, 2, and 4, and we always subtract the pivot coefficient, 5 over 4, multiplied by the corresponding value in the pivot row. Let's see what this comes out to be. So we're making progress now. We've eliminated all the values in the first column that are underneath the diagonal. The only value that's left underneath the diagonal of this matrix is the negative 0.5. So let's go ahead and eliminate that. Now we'll be using the same formula, new row equals old row minus pivot coefficient times pivot row. But what we need to be aware of is that our pivot value has changed. Remember, the pivot value is always the value in the diagonal that is above the value you're trying to eliminate. Since we've moved over one column to the second column, our pivot value is now negative 0.25, since that's the value in the diagonal that's above the value we're trying to eliminate. And consequently, our pivot row has also changed. Since our pivot value is in the second row, the pivot row is now the second row. But it works the same way. The new row is the old row, 0, negative 0.5, 2.59, minus our pivot coefficient, negative 0.5 over negative 0.25, times the pivot row, 0, negative 0.25, negative 0.325, negative 6.5. So we'll go ahead and write this out. Once again, each value, we're starting with the old value and subtracting the pivot coefficient times the corresponding value in the pivot row, which is the second row in this case. And we work out the math we have successfully eliminated all the coefficients beneath the diagonal of this matrix. So we've created a matrix that's what we call right upper triangular, since all of the values are in the right upper hand side of the matrix. So what do we do with this matrix? Now recall that this augmented matrix is just a shorthanded way of writing the entire system of equations. And the whole point in performing forward elimination and converting so many things to zero was to make it easier to solve for our variables x3, x2, and x1. And we will solve for them in that reverse order, starting at the bottom and working our way up. If you think about the way the matrix math works, you can see that when we multiply the bottom row of our coefficients 0, 0, and -4 times our variables, we'll only have one variable to deal with. And this works out to be -4 times x3 equals -4. This means, of course, that x3 is equal to 1. Great, we've solved for one of our variables. Let's keep working our way up now and solve for x2. The matrix math on this will work out to be -0.25 x2 plus 3.25 x3 equals 6.5. But we already know that x3 is equal to 1. So when we substitute that in, we end up with a value for x2 equaling -13. Well, what comes next? You guessed it. We'll go ahead and solve for x1. This equation has all three variables, but once again, we've solved for the two unknowns, x2 and x3. When we plug everything in and rearrange for x1, we find that x1 equals 3. Now all we have to do is check and report our answer. x1 is 3, x2 is -13, and x3 is 1. If we bring up the original system of equations, you can plug in these values in place of the variables and check to make sure that the matrix math makes sense. Or of course, you could simply substitute them into the original equations and check that way. It amounts to the same thing. Best wishes on solving your own systems of linear equations by Gaussian elimination.